we're going to perform next Tuesday, waters of constitution and hydration. It comes in two parts. Waters of hydration is the first part of the experiment. The second part of the experiment is waters of constitution. Waters of hydration are those where the water exists as water molecules in the structure, the crystal structure of this ionic solid. They are independent water molecules, so we write them this way. The waters of constitution are those, we don't know that the water's there until we heat the material up and dry the water off. So the water actually forms out of the structure of the compound during the process of heating. The water's not there until you heat it. And we're going to use, for the C part, right? The A part we don't do because that's a flame test, and flame tests never work. So I'm just telling you, this is your starting point. For this one, we're going to use baking soda, sodium, hydrogen, bicarbonate. Notice, but you do have hydrogen and oxygen. So that's where the water comes from. When you heat it, some of that hydrogen recombines with some of that oxygen and makes water. It makes something else too. And that's going to be the detective story, finding out what that something else is. This is the easy one. You know it's this plus some water. So all you have to do is heat that up, right? Just like the method calls for. Let it cool down in your desiccator. When it reaches room temperature, take it to the analytical balance and find out the mass of the empty container to 4 decimal places. Right? So you're going to have a table, construct a table that has the mass, empty crucible, right? Mass of empty crucible, grams. Then you're going to put a certain amount of this compound in there with the water. And they say approximately 1.9 grams. So this is the mass of the crucible plus the hydrate. That's what we call that. The hydrate is the compound with water. Okay, what can you determine from those two? You can determine the mass of the hydrate. You know this mass, you know this one, plus the hydrate, just subtract this one from this one, right? And so this one will be the mass of the hydrate. By subtracting this one from that one. Now, if you try to subtract this one from this one, what are you going to get? A negative number, right? So it should be pretty obvious if you try to do it that way that you got the wrong answer. Subtract this one from this one. You get the mass of the hydrate, okay? So now what we're going to do, we're going to heat it up over an open flame. Okay, what's that going to do? That's going to drive off all of this water. Now, the melting point, the range of temperatures here is very broad, right? It's very forgiving chemical. You can take this up to pretty high temperature. I forget what it is, 600 or 700 degrees Celsius, before it starts to decompose, right? And then you've got a different reaction. But you can heat it up really high and get rid of all that water. And what do you have left over? Well, now you've got the anhydrate. So now you started off with a certain amount of this hydrate. Now you got a little bit less. And why? Because you drove off all the water. So how much water actually left? Well, you need the weight of this one subtracted from the weight of that one. And that's the weight of the water, the mass of the water. So what do we got now? Well, we got this hot crucible with product in it. You gonna stick it on the balance? No. You stick it on the balance, the weight's gonna be like this. It's gonna go up and down and up and down and up and down. Air currents everywhere. You put it back in the desiccator and let it cool. Right? And this is even more important than before, because if you let it cool down in the air, it's going to suck up more water. Right? You want it to cool down in 0 humidity. So now when you weigh it, what are you going to have? You're going to have the mass of the crucible plus the anhydrate. And means not. No water. Okay. Now, what's the mass of the anhydrate? Well, you just need to subtract the mass of the crucible, don't you? So you subtract this one from that one. And that's the mass of the anhydrate. Okay, so we did all that to find out the mass of the hydrate and the mass of the anhydrate. Okay, what's the difference between these two? This one's got water in it, that one doesn't. This one weighs less than that one because it lost water. So if you subtract this one from that one, what is that? That's the mass of the water. Okay. Now, how many moles is that? Divide that by 18.02. Right? If you got the mass of water and you want to get rid of the mass and change it to moles, right? Numerator, denominator. So many moles, 18.02 grams. Divide that into this value. That's the moles of water you have. Correct? Okay. How are you going to relate that to this? You need to know the moles of that, don't you? So how do we find the moles of this? Well, the mass of the anhydrate is this right here, isn't it? So you look up copper, sulfur, 4 oxygens, add them together. Right there. That's the molar mass of this compound. Divide it into this one. So this one you're going to convert to moles. And this one you're going to convert to moles. And then ratio them. Right? If you divide one by the other and you get a decimal fraction, what does that mean? That means you put the wrong one on top. Just flip them. And estimate to the nearest whole number. And that will be X. Okay. Any questions about that part? That's the easy part. That's the easy one. The bicarb is a little more difficult. Okay. So that's the first part. And if you set this table up like that, in your book, in your lab book, and you know a number goes in there, at least one. Does it say we're going to duplicate that experiment? I hope not, because there's really not enough time. No, it doesn't say repeat it, I don't think. Okay. Also in that document, you'll see discussion pages tacked to the back. That the first discussion is the one I just gave you right here about the copper sulfate. with sample calculations. Don't use those calculations for yours because you're going to have different values, but that gives you an idea of how it works. Part 2. All right. I probably shouldn't have erased all that, but be that as it may. You're going to do the same type of experiment here. Only, oh, by the way, that blue color, that pretty blue color you start out with, when you get finished with that one, it's gone. It's a white, crusty powder, right? The water in that crystal structure is what gives it the blue color. Get rid of the water, it's nothing but a white powder now. Okay, that's how you know that you completed the burning process. With this one, it's a little different. You have to look more for texture. Or just follow the instructions and heat it for as long as they say. And then maybe add a couple of 3 minutes to be sure that the conversion is complete. So if there's no water here, we can't use that same reasoning that I just gave you for the copper sulfate hydrated. It doesn't work because we don't just get rid of water here. There's also possibility of getting rid of some other oxygen and maybe even carbon. We don't know. So we have to propose possible reactions. Right? You're going to go through the same process, maybe with a different amount. Let's see. I think it says use a different amount. Instead of 1.9 grams, 2.5 grams. Okay. I want you to put a little bit more in there. So it's going to take a little longer to do that. And once you heat it, you're going to have a table with the crucible, right? You're going to have the crucible plus the sodium bicarb, right? And then when you heat it, you're going to have, well, you can subtract those and get the mass of the sodium bicarb. Like that. And then when you heat it, you're going to have another weight, which is the crucible plus the burned compound. We don't know what it is yet. Okay. So we're going to go from, and then here you have the burned compound. After you subtract the crucible from this one, that gives you the burned compound. Crucible from this one gives you this one. So here's your comparison. It started out at 2.5 grams here, roughly. You're going to know exactly 4 decimal places. And here is what's left over. So it should be less, obviously. But what are the possible reactions? Well, that's where the discussion kicks in. Page part 2, page 2. Right? You have some solid left over. Right? There's no liquid. It's all solid. So one possibility is an intermediate explanation. Right? If you have this, and you're going to make water, right? And you can take my word for it. There is water that's evolved. That's been determined. And you can take a mirror and put it over the reaction vessel and see the water condensing as it rises. As you heat it, there will be water. So you know water's coming out. But it may not be the only thing. But we do have water. And then what's left over? Well, let's see. if we get rid of all the hydrogen, then we say that we only have sodium, carbon, and oxygen left over. Right? And they use a little symbol here like this, the delta. That means heat. But in order to write to balance this equation, we've got two hydrogens here, right, for this water molecule. So that means we need at least two over here, don't we? Right? Okay. That means we need at least two over here. And two hydrogens here used up, two carbons, and we're using one oxygen here, so that means we have 5 left over here. I think that's where they get that. Yeah, that's where that came from. We start with two hydrogens here required, so we have to have 2 of these. And then we just put the rest of them minus this one over here. So this is like our intermediate. That's not a real compound. We're reasoning through it. So that's where we are at this point. So we're saying, what could this possibly be? The other types of compound that could come out of this one is where we're at now. So we could say that this one actually could have carbon monoxide come out of it. And if that's the case, then we still have 2 sodiums, we have a carbon, and we have 4 oxygens. 4 oxygens. Na2CO4. Right. Or but this looks like a an ionic compound, doesn't it? So if this is plus, and we know that CO4 would have to be 2 minuses, right? That's the only way that we get balance, 2 pluses with this one, 2 minus. So if we look at this one, 2 minus, and we look at the oxidation states, we've done that before. We've done oxidation states yet? In the chapter 2? We haven't done that yet. I think it's the next chapter. Okay, let's look at it as charges then. So what's charge on oxygen? It's usually 2 minuses. 2 minus times 8 times 4 is 8 minus. And hold these 2 out. So that means 6 minus has to be balanced by 6 plus. 6 plus for carbon is impossible. The most carbon can go is 4 plus, right? Because it's in a valence position here. 1, 2, 3, 4. So it can either be 4 plus or 4 minus. No other options. So that's why this one is out. 6 plus is impossible. So what if instead of 1 CO, we pull out 2, right? Because we've got 2 carbons here, don't we? What if we make 2 carbons here? Excuse me, 2 COs. Now we have 2 carbons and 2 oxygens. So Na2, and then we have no carbons. Right? We've used them up here. And then we've used 2 oxygens, which means 3 here. Right? So now, if this is 2 minus, then that means 6 minus, and 6 plus here. So sodium would have to be 3 plus, wouldn't it? That can't happen either, because sodium's an alkali metal, and they're always +1. No other options. So that one's out. So that means carbon monoxide is probably not the other gas that comes off of this. Why are we even bothering with this? Because this is not a real compound, right? If we looked at the balance of charges in here, it doesn't exist. So there has to be something else come out of it. And sodium's not going to come out because we're not hot enough. Right? Sodium's going to be left behind in some form. So it has to be a carbon-based compound. What if instead we pull carbon dioxide out of that? CO2. All right, now what's left over? Let's see, we still have sodium. We still have 2 sodiums and 1 carbon, excuse me, one carbon left over, 2, then we have 3 oxygens, Na2CO3. Okay, let's see if I did that right. 2 sodiums, 2 carbons, 1, 2, 5 oxygens, 2, yeah, okay, so that's possible. Now, is that possible? Well, if CO3 is a polyatomic ion, it's 2 minus, right? And this is 1 plus, which means 2 plus total. So that's possible. That could be our compound right there, Na2CO3. What else? Well, we can follow our example from carbon monoxide and say, what about 2 carbons? What if we pull 2 CO2s out? CO2. Okay, now we got rid of all our carbons. So that means we have Na2, and we have 4 oxygens here required. 2 times 2 is 4. That means we only have 1 oxygen left. Is that possible? Well, this is 2 minus, and this is 1 plus, so that's 2 plus. Yeah, that's possible too. So either one of these is possible. Okay, so how do we tell the difference between the two? Well, there are 2 ways. There's a quantitative way, and there's a qualitative observation. And you're going to do one in the lab. It's called the fizz test. Okay. If you take the solid, if this is a gas, it's gone. The only thing you have left is this or this. So if we add 1 molar hydrochloric acid to that solid, what's going to happen? Well, if it's this one, 3 plus HCl, what do you get? Well, you get hydrogen exchanged with sodium, and you make, actually we need 2 of those. You have 2 sodium chlorides, right? 2 chlorines, 2 sodiums. We have 2 hydrogens. Excuse me, H2CO3. There we go, that's balanced. This is carbonic acid. Carbonic acid doesn't like to stay like that. There will be some of it in solution, but some of it will want to do this. It'll want to do H2O plus CO2 gas. There's your fizz. You'll see bubbles. If you add hydrochloric acid and this is your product, then you'll see bubbles come out of it because of this reaction. Now, you run this reaction in reverse, what do you get? Soda pop. You put carbon dioxide under pressure under water, and some of it goes into solution, but some of it reacts with water and makes carbonic acid. Okay. That's why Coca-Cola, if you put a nail in Coca-Cola, one of the reasons, not the only reason, then in a week or 2, the nail's gone. Coke would just eat it up. Now, the other reason that happens is not just the acid, but it's the phosphate, because they put phosphates in Coke also. And iron and phosphorus just love one another. So acid in combination with phosphate means your nail is gone. Anyway, so this is a possibility. So what if we add acid to this one? Na2O HCl. Okay. Well, how's it going to make a fizz out of that? Well, it can. This cation is going to combine with that anion, like that. But there are two of them, right? So we need two sodiums, which now we need two chlorines. So what's left over? Well, two H's and one O. Right? It just makes salt water. No fizz. So if there's no fizz, then this is your product. Okay? That's the fizz test. That's the qualitative observation. Okay? The other one, and it'll take too long to do the calculations up here. That's why I put them down. I put them in here. Quantitatively, if we write the equation, now we're going to substitute here. Let me erase this. So we could write two possible equations here. This heated produces water plus CO2. If it produces one CO2, and this one 2 CO3, that's the one that gives you the fizz. Remember, that's the solid left behind. Or it could produce this. Like that. Then we need to balance it. Let's see. 2 sodiums. 2 sodiums. Let's see. 2 hydrogens. There's 2 hydrogens. Yeah, that's good. 2 CO2s. 2 C's. 2 N2s. Oh, that's good. This one's balanced. How about this one? Let's see. 2 sodiums. 2 carbonates. 2 hydrogens. That one's not balanced. Oh, yeah, it is. Let me back up and look at it again. 2 sodiums, 2 sodiums, 2 hydrogens, 2 hydrogens, 6 oxygens. 1, 2, 3, 4, 5, 6. Okay, yes, balanced. Okay, the reason I wanted to balance those is because if you start out with 2.5 grams here or here, it's going to give you a different amount of product, isn't it? And you know the mass of these products. So if you use stoichiometry and say, if it's this one, then it'll give you a certain mass of that one. But if it's this one, it'll give you actually a lesser mass. And you compare those values to the one you actually get in the experiment. And see if it's closer to this one mass or this mass. And that's confirmation that you've picked the right overall reaction. Okay, does everybody see that? Or your head has to stop spinning first, and then you can see it. So, any questions? Oh, we didn't work out the pre-lab question. Here we go. Let's start that one rolling. I'm starting. This thing's running out of ink. Let me see if this one works any better. Okay, pre-lab question. You're given a sample of gypsum. You know what that is? Wallboard. All modern homes are made with gypsum wallboard. That's what's in your walls. It's just sandwiched between two layers of paper.
Like drywall?
Yeah, drywall. That's gypsum. Okay, we know that gypsum has this formula. And then it has some water in it. Okay. We want to determine that ratio. How many waters per mole of calcium sulfate? And we're given a crucible that weighs 38.0160 grams. 38.0160 grams. This is the crucible. And we heat it up. Oh no, this is the crucible plus gypsum. And the crucible weighs 33.0160. 33.0160 grams. How convenient. Somebody must have made this one up. That'll never happen. After heating the crucible over a flame and cooling in a desiccator, the crucible and contents weigh 36.9405 grams. So now the crucible plus anhydrate. Actually, they call it anhydrite, excuse me. The anhydrite weighs what? 36.9405. 36.9405 grams. Okay. How much gypsum did you have there in there originally? 5 grams. Right. Subtract this one from that one. How much anhydrite do you have in there now? Subtract this one from that one. Which is what? I'll see if I can do it on the board. 5, 5, 4, 11, 7, and then 9 from 9 is 0. And 2.0755 grams. So what's the difference? Well, the difference is the amount of water that was lost. Correct? We're going to have picture time.
Can you interrupt your space?
Oh, sure.
Thank you. Y'all don't mind me. All right, so what are you teaching me today?
Oh,
Yeah, you're
we're-
gonna teach me something.
we're doing a review. Not a review. We're doing a discussion of a lab that we're going to do next Tuesday on this topic, waters of constitution and hydration. And we've run through the procedure already. Now we're doing an example problem that's in the method.
Okay.
Okay, so we have this compound, which is calcium sulfate, and each molecule of calcium sulfate has attached to it a certain number of water molecules. And we want to determine how many of those for each one of these. So this is the data set that we were given. We have this crucible that we've weighed. Here's the weight. And then we add some of this gypsum, which is the water containing compound, gypsum, to that crucible and weigh it again. So now by subtraction, we can find out how much of that gypsum is in there. Okay. Then we're going to heat it up.
Just come sorry, a little bit over closer.
Absolutely.
Okay, we're going to heat it up and drive off all the water. And now we have left behind is what we call the anhydrite because it has no water in it. And that's the crucible with the anhydrite in it is this way. So we can find out how much of the anhydrite is left simply by subtracting the crucible weight from this. And these are the differences This is with the water, this is without the water. And subtract those two from each other, and you find out how much water it is.
So that makes sense to you all? How would you back there?
That's fun. When you showed up, I was pausing for their heads to stop spinning.
Yeah, I understand that.
And that was, and I felt it was a perfect cue for me to ask a question.
Absolutely.
It'll make-
Absolutely.
It'll make more sense when you get in the lab and actually do it.
And you start heating all of the stuff.
Right.
And
Right, we're gonna use an open flame. Everybody likes fire, correct?
does
Okay.
it explode?
No.
Oh, that's
It
no fun.
it could pop, so we have a little lid that we put over the top of it.
I like explosions, but that's just me.
I feel like now we need to follow up for the lab
I know,
portion
now
to see what's gonna
it's-
happen.
Next Tuesday.
Okay. Yes, but I,
Okay, you mind if I picture your thing, so we-
Oh, yeah, sure.
Put your name in there too. And this is a, which class is this?
This is chemistry.
Chemistry?
Yeah, there
One
it
of
is.
them. There we go. Okay. Thank you so much.
Yes.
okay.
You're gonna see the back. Did you see the backwards jacket?
Oh,
He was the soil guy.
this is the former life.
This is his other life.
Okay.
Thank you all. And you'll get it. I know you will.
Okay, so now if we subtract this one from this one, that's how much water was lost in the process. So let's see, 2.0755 is 2.925. .245 grams, and this is the water that was lost from this much of the gypsum. But we want to relate this amount of water to that amount of anhydrite. So we need this one to be converted to that many moles, and this one to convert to that many moles. So this one, we know how to do that. Grams per mole. Okay. But for this one, yeah, the anhydrite, we need 2.0755 grams, and this is the calcium sulfate, the anhydrite. So we need a molar mass for a calcium sulfate. Right, let's see, calcium is 40.08, 40.08. And then we have one sulfur here, 3207. And then we have 4 oxygens. 64. So that's 136.15. 136.15. Okay. So now I've already got that in my calculator, so I'm going to do this one first. 2.0755 divided by that number is 1.25, excuse me. I'm dyslexic. 1.524 times 10 to the minus 2 moles of this compound. And water is, let's see, divided by 18.02 is 1.623 times 10 to the minus 1. So we just need to ratio those two. So if we're looking for a whole number here, not a fraction, but a whole number, which one we divide into it? Now this one, that one. This one's smaller than that one. So let's see. I just need to swap these and I can do it. They're already in my calculator. Divide this one into that one. And I've got 10.6. 10.65 to 1. Something's wrong. Why do I know that? Because I know what that number needs to be. So let me check my math here. This is right here, isn't it? 380160. 380160 and 330160. The crucible. And then 36.9405. Yeah, those numbers are right. This number should be, those all cancel out, so that's correct, that's 5. This one needs to subtract that number, so let me do that. I did that in my head, and that's probably where the error is. And 36.405. Let's try that again. 36.9405. Crucible. And subtract the crucible. 33.0160. 3 point, okay, that's where it is. That's my mistake. It should be 3.9245. $3.9245 divided by 136. This one's right. 6.15 divided. Okay, this is 2.882 and 10 to the minus 2 divided into 1.62. Let's go. 5.6. That's still not quite right. But you get the idea. Run that. Let's see, did I do that one? No, I let that one too fast. It's supposed to be 7. The accepted value for X is 7. So check my math. All right, don't take my word for it. Do these calculations yourself and see what you come up with. I'm not sure why it's doing that. Unless I did one of these calculations wrong also. Oh. That is wrong. Because it was based on that earlier number. Right? This one subtracted from that one. If you got to go ahead. 1.0755.
Thank you very much.
5 divided by 18.02 is 5.968. 5.968 times 10 to the minus 2. That's not right. Hold on a second. 1. Oh. .02. Yeah, that's right. Did I do this one right? 3.9245. 136.15. 2.88. It's 2. Oh no, that's not 7. What am I thinking of? I'm thinking of zinc sulfate. That's right. So you can see that ratio is about 2. The closest whole number ratio there is 2. So X equals 2.